page number?
This is from the handout I gave.
Okay, oh, that's the pink one, sorry.
Yeah, the pink one. Somebody put the printer with pink paper, so it came out in pink.
It's fun.
So the review of concepts from canceled classes. This is a review from those videos that I asked you to watch for extra credit. Let's go over this one problem here, and it involves the reaction quotient Q. Okay, so we already talked about K, which is an equilibrium constant. Okay, this is capital K, not lowercase k. Okay, we do not put solids, we do not put liquids in K. Yeah, apps don't do that. Students will do that and get points deducted. And this is products over reactants, okay? Each raised to its coefficient, so you always balance the equation. Okay, so you take the products, each one is raised to the coefficient, whatever that number is, you use to balance. Same thing for each of the reactants. Okay, so this is K. This tells us where the equilibrium, you have more of products, or the equilibrium you'll have more reactants. If your K is equal to 1, you have neither. So it's like 50-50. Okay, products and reactants equal to 1. Okay, this is unitless, and what else? No solids, no liquids, right? And then the final thing, it's quoted at a specific temperature. Okay, so now I want to teach you guys this concept called Q. Okay, so we're going to, Q has the exact same equation as K, which is products over reactants. However, there's a difference. So here, when you're dealing with the reaction quotient, we have to ask ourselves the question. So let's ask ourselves this question. Okay, we're asking ourselves this question here. So okay, we're going to ask ourselves the question this. Okay, we ask ourselves, is the reaction at equilibrium? Okay. Is the reaction at equilibrium? If it is not at equilibrium, at equilibrium, okay, which way will the reaction proceed? Which way will the reaction go to get to equilibrium? Which way will the reaction go to get to equilibrium? Okay, so for this we have to compare Q to K. Okay, we will compare Q to K. So we ask ourselves the question, is this reaction at equilibrium? Okay. If it is at equilibrium, Q will equal K because it's the same equation. It will equal the equilibrium constant. So we ask ourselves the question, is the reaction at equilibrium? Okay. If it is not at equilibrium, which way will the reaction go to get to equilibrium? Okay, so we're going to compare Q to K. Okay, so we're going to use something called the Gator rule. Okay, have you heard this this term? Okay, this is how I learned it. It's called the Gator rule or alligator rule. For me to teach you this so that you get the right answer on the exam, you have to do this. You have to put Q first. Okay, you're going to put Q first and then compare to K. Otherwise, what I'm telling you is wrong. Okay, so put Q first. Okay, you want to put Q first. Okay, and then you compare to K. So Q, Q, Q. Okay, equilibrium constant K, K, K. All right, so there's three things that could happen. Okay, Q can be greater than K. Okay, Q can equal K, and Q can be less than K. Okay, when you compare Q to K. Okay, bless you. All right, Q can be greater than K, Q can equal to K, or Q can be less than K. Okay, so if Q is greater than K, pretend this is a gator claw, or gator, whatever, gator chomp. Okay, which way is the gator chomp pointing towards? The reactant side or the product side? Which way? Reactant side. So are you at equilibrium? No. Which way will the reaction go to get to equilibrium? Left, or the reactant side. Okay, so reaction not at equilibrium, it's going to shift to the reactant side or the left to get to equilibrium. Shift to the reactant side to get to equilibrium. Okay. So here R is reactants, or the left-hand side. Okay, if Q is less than K, where do the gators go? Gator claws? To the product side or the reactant side? Correct. They're going to shift to the right, which is the product side. So you're not at equilibrium. Where will the reaction go to get to equilibrium? Products. Kind of like Le Chatelier's principle. Okay, you shift this way or you shift that way. Some of you change colors, pink, blue. Okay, this is pretty much what that is. Yes, you're correct, Sam. If you are not at equilibrium, to get to equilibrium, it's going to shift to the product side. To get to equilibrium. Okay, if Q is equal to K, then what? Okay, you are at equilibrium. So it equals to the actual equilibrium constant. Okay, whatever that may be. Okay, it equals to the actual equilibrium constant. So those are equilibrium concentrations. So it's not going to shift anywhere. Okay, you are at equilibrium, wherever it may be. This way, or K is equal to 1. Okay, whatever that equilibrium constant is for that reaction, you're at equilibrium. So this Q versus K, Q is called the reaction quotient, tells us where it will go to get to equilibrium. This was the whole idea behind the lab that we did Monday and Tuesday. Okay, if a reaction is at equilibrium, okay, and you disturb it, okay, it's going to go back and shift to where it originally was from. Okay, maybe the reaction was here, you disturb it, it will go back to here. Okay, so wherever it goes to get back to its the original equilibrium. That's why, or that's the purpose of using Q. Alright, so with that being said, let's go ahead and solve this last review problem involving the reaction quotient. And then what I will do is we will continue on with our notes. Okay. All right, so the equation is here. Are we at equilibrium? Is this an equilibrium reaction? Yes or no? Okay, we are at an equilibrium reaction. Okay, so this reaction is at equilibrium. And it's asking at a given temperature Kp. Now this P in the Kp stands for pressure. Okay, and that's going to equal to 2.7 in this problem. And if 0.13 moles of CO, 0.56 moles of H2O, 0.62 moles of CO2, and 0.43 moles of H2 are put in a 2-liter flask, in which direction will the reaction proceed? Okay. So K here, the P stands for pressure, but notice here they're giving moles over liter. Okay, everyone see that? Moles over liter. Okay, moles over liter. Moles over liter is concentration. So before we do anything, let's calculate Kc. Okay, Kc. Because we know here that Kp is going to equal to 2.7. Okay, but that's pressure. Okay, we have a bunch of gases. And the gases can be expressed in terms of pressure, which is what this K equilibrium is, and concentration, which is what we're given concentration. So the first thing we should do is we should calculate the concentrations of each of these. Okay, the equation, I'll give you the equation on the exam, is this. Okay. Equilibrium concentration in terms of pressure is equal to equilibrium concentration in terms of concentration times RT raised to the power of delta N. All right, we already got Kp, but we need to get Kc for this. All right, let's calculate the concentrations first. All right, we'll first do the concentration of, is this balanced? Yes, it's balanced. Okay, good. All right, let's do the concentration of H2 here. Concentration of H2 is 0.43 moles divided by 2 liters. Okay, 0.43 moles divided by 2 liters is 0.215 molar. Let's do the concentration of CO2 product. CO2 is 0.62 moles divided by 2 liters, and this is going to be 0.31 molar as the concentration of CO2.
If it wasn't balanced, we have to balance it first.
Yes, you'll have to balance it first. Yes, very much so. All right, let's do H2O. H2O is 0.56 moles over a liter over 2 liters. And what is that? 0.23, what is that? 0.28, sorry. And then finally, let's do CO. Okay, this is 0.62 moles divided by 2 liters. This is going to be CO, right? This is 0.13, I'm sorry. 0.13 mole divided by 2 liters, and this is 0.065 molar. Alright, so we have our concentrations. Let's go ahead and calculate the equilibrium constant for this reaction. They are all gases, and we'll calculate the Kc. So Kp is 2.7 equals Kcr is 0.0821. Okay, T, they don't give us a temperature T, but that's okay, because what is delta N? Okay, it's the moles of gas products minus moles of gas reactants. Okay, remember this from Monday's class? Okay, so how many moles of gases do we have in the product side? 2. Okay, how many moles in the reactant side? 2. Very good, Susanna. So 2 minus 2 is 0. So all of this is to the 0 power. Okay, what is anything raised to the 0 power? 1. So Kc is equal to 2.7. Okay, when there's no change in the number of moles in the reaction, the Kp is equal to Kc. When there's no change in the number of moles of the reaction. Alright, so now we have our Kc here, equilibrium constant, in terms of concentration, and that will be 2.7. We got our concentrations here. Let's plug that in to the equilibrium expression. Okay, so the equilibrium expression is going to be this. It's products over reactants. Alright, so Kc is equal to the products, H2, okay, raised to the 1 power, it's balanced, times CO2, okay, raised to the 1 power, it's already balanced for us, divided by the products, concentration of CO times concentration of H2O. Okay, this should equal to 2.7. Right? This should equal to 2.7 because that's what we calculated Kc to be. That's what we want them to equal, 2.7, because that is what Kc is. Equilibrium constant in terms of concentrations. All right, let's plug stuff in. 0.215 for H2. Okay, there's no units, so I'm not going to bother with the units. CO2 is 0.31. What is CO? 0.065. And H2O is 0.28. So this should equal to the equilibrium constant, which is 2.7. Okay. So let's check this out in our calculator. 0.215 times 0.31 divided by parentheses 0.065 times 0.28. Close those parentheses, and I'm not getting 2.7. Something is not right here. I'm getting 3.7. Alright, so it does not equal to the equilibrium constant. So the question I have for you guys is, are we at equilibrium? No. Which way do we have to go to get to equilibrium, left or right? Alright, so remember, in the Gator rule, put Q first. Okay, the Gator rule, put Q first. So what is our Q? Okay, and what is our K? Okay, that's given to us. Okay, we calculated it from Kp. Kc is 2.7. And which is bigger, 3.7 or 2.7? Okay, which way is the Gator chomping? Okay, so we're not at equilibrium. Where will the reaction shift to get to equilibrium? To the reactant side or to the left. Okay, so this is the direction in which the reaction will proceed to get to equilibrium. So we're going to write here the reaction is not at equilibrium. Okay. It will shift to the left, or it will shift reactant side to get to equilibrium. So this is what you'll do on an exam, okay? You'll put Q and compare it to K. Okay? In the Gator rule, what do we put first? Q or K? Q. Okay? What is the equation of Q? Same as K. We're just comparing. Okay? We're just comparing the numbers. And if Q is equal to K, which was 2.7, we're at equilibrium, okay? It's not going to move anywhere. But it's not equal to K. It's not equal to our equilibrium constant. So it's going to move so that it can get to equilibrium.
Is the answer not 38 for KC? You said it's 3.7?
2.7 is KC.
No, K or K when we solve for, it says 3.7. Is
Right.
that equal to 2.7?
Correct.
Where did we get the 3.7?
I plugged in these values here.
We want it to equal 2.7. So
But
it's not, but it's
Correct.
equal to 3.7.
Correct. So that's why you're not at equilibrium. You're right. Because it doesn't equal to 2.7, are you at equilibrium? No. Which way will it go to get to equilibrium? Okay, put Q first compared to K. The alligator jaws point to the reactant side. So it's going to shift to the reactant side to get to equilibrium. Right. All right, any questions on this? I'll let you, I'll give you a couple of minutes to see until you get it. I'll wait for you to give me the thumbs up. Is that okay? All right. All right, so this sort of reviews all those videos that I made you watch, because last week we did not have much of class. And now let's go back to our normal notes, our normal routine, our normal notes, right? So this is a good study guide for the exam, so problems will mostly be like this, right? So if you know how to do these problems, I think you're good in terms of the test. I think the test is after spring break, so you still got a while. So that again?
After spring break?
Yes.
It's dangerous.
Dangerous? Why is that
It's
dangerous?
not. It'll give us plenty of time to prepare.
Okay, I'll make it before spring break. I'll make it next Friday. I won't do that. It'll be after spring break. Because everyone has midterms or something. Right? No? Whatever it is, it's going to be after spring break. The week after spring break, though, so if you're going to the beach, okay, make sure you come back from the beach and then study, okay? All right, let's do one more of these reaction quotient problems, and then I'll teach you something new. The new thing I'm going to teach you is called the ICE table. I remember growing up, because I grew up in Florida, spring break was like a big deal. Like everyone would advertise things in the beach, going to the beach or Daytona and stuff, or what have you. So whenever I think of spring break, I think about the beach. I never went because I was staying at home studying.
I do have a question. Because, like, I get that this was the, like, we wanted to equal 2.7, but, like, why would we do this right here, like the KP equals KCRT delta N, if we know we want it to equal 2.7? Like, why can't we
No,
just get that?
because these are concentrations, not pressures. These are concentrations. The KP, the P stands for pressure. And these are concentrations. Actually, we had to calculate the concentrations going moles over liter. So we can't just, it just happened to be that Kp and Kc are equal. No, it happens to be that Kp, the equilibrium constant in terms of pressure, is equal to the equilibrium constant in terms of concentration, which is 2.7. They're not equal because these are not the equilibrium concentrations. Okay. Concentrations, you look at Kc. Okay. If these were pressures, you look at Kp. They just happen to be equal because of this equation. There's no change in the number of moles of gas. That's another thing that's tricky about this problem. They give you a Kp and they give you concentrations. So you need to get Kc utilizing this equation. That's why this is a little bit more trickier than the other ones. This one is a little more straightforward. It's the same principle, so let's go ahead and do that. All right, we'll do one more reaction quotient problem, and then we'll talk about ice tables. All right, so the Kc, what does Kc stand for? They sound alike. Okay, C stands for concentration, and your name is also Kc. Okay, the Kc for this following reaction is 6.5 times 10 to the 4th at 35 degrees C. All right, a certain experiment, 0.020 moles of NO, 0.0083 moles of Cl2, and 6.7 moles of NaCl are mixed in a 2-liter flask. In which direction will the system proceed to reach equilibrium? Okay, so they give you a Kc, and they give you moles, and they also give you liters. So I say let's calculate the concentration, because our equilibrium constant is in terms of concentrations. Okay, are we in an equilibrium reaction? Okay, always look at your arrows. Okay, be very cognizant and observant of your arrows. This is definitely an equilibrium reaction. It does not proceed to 100%. All right, first thing I'll do is calculate all these concentrations first. NaCl is 6.7 moles divided by 2 liters. What is 6.7 divided by 2? 3.35 big M. Cl2 0.0083 moles divided by 2 liters. That's 0.00415. Am I correct? Okay, I hope I'm doing my math right. And then we have NO. NO. This is nitrogen monoxide. And this is 0.020 moles. Divided by 2 liters, and this is 0.010 molar. All right, what is Kc? Okay, it's products over reactants. Okay, NaCl. What should we do with that NaCl? What should we do with that NaCl? Okay, what do you think about that 2?
Square it.
Excellent, we should square it. Products over reactants. Cl2, what should we do with that Cl2? Is this balanced? Yeah, it's balanced. Okay, what should we do with that Cl2? Okay, raised to the power of 1, and this NO, what should we do with that NO? Okay, we should square it. Okay. So if we are at equilibrium, what should this expression equal to? Okay, Okay, if we are at equilibrium, which we do not know, but if we are at equilibrium, this math should equal to 6.5 times 10 to the fourth. Okay, we don't know if these concentrations, when we put it in here, equal to 6.5 times 10 to the fourth, but let's plug it in and see. Okay, so we have 3.35 squared. Cl2 is 0.00415. And NO is 0.010, and then we gotta square it. Alright, so what is this on our calculator? 3.35 squared divided by parentheses 0.010 squared times, I hope this works, 0.00415. What is that? 2.7 times 10 to the 7th? I can't even see this. Is it 7? Yeah, 2.7 times 10 to the 7th. Okay, do that again here. Okay, 2.7 times 10 to the 7th. So obviously they're not equal to each other. So since they're not equal to each other, are these equilibrium concentrations? No. Which way will the reaction shift to get to equilibrium? Okay, we're going to put Q first. Okay, put Q first, then compare to the K. Q is 2.7 times 10 to the 7th. What's K? Okay, K is given to us in the problem as 6.5 times 10 to the 4th. Which is bigger, 10 to the 7th or 10 to the 4th? Okay, 10 to the 7th. So Q is bigger. Okay, right? So I put all this in. I got 2.7 times 10 to the 7th. It's not at equilibrium. Okay, so this will be my Q. K is given to us in the problem, as it will be. And which way will the reaction shift to get to equilibrium? The reaction will shift to the left, to the reactant side. Very good. Okay. One thing I want to tell you guys is don't forget your exponents. Okay? So this is a way you can get the problem wrong if you don't use the law of mass action. Okay? So the square comes from this 2. The square in the NO comes from where? It comes from this 2. Okay? Alright, so the same thing as we did in the previous problem. We have our Kc, we got our concentrations, we compared Q to K. This Q, once again, is called the reaction quotient. Okay, Q is the reaction quotient. And if you want to use the Gator rule, which should go first? Q should go first. Okay? So let's go to a new topic that I want to teach you guys. Okay, and this is called the ice table. Okay. So this is another new concept in Chem 2 that you probably have not seen before in Chem 1. So it takes a little bit of practice, but I think it should be okay. So the first time around we'll do it, we'll get our feet wet, and then we'll do some problems where this will become very routine. Okay? So we're going to construct an ice table here for these equilibrium problems. Ice table. Okay, so what does an ice table stand for? Ice, the I in ice stands for initial. The C in the ice table stands for change. And then the E in the ice table stands for equilibrium. Okay, so in these types of problems, we find the equilibrium concentrations. Okay? Okay, find the equilibrium concentrations at the end of the reaction. Let's do an ice table problem here. And we'll see one of these on the exam. So I'll put 3 stars here. Alright, so let's go ahead and do this. And doing this will make more sense than me explaining it. Alright, starting with an initial concentration of 0.040 HI, hydrogen iodide. What is the equilibrium concentrations of H2, HI, H2, and I2 at equilibrium? All right, so here they give us the equilibrium constant at 740 Kelvin. All right, so first thing we will do is construct our table. Okay, construct our ice table. So I'm going to rewrite this problem here. H2 plus I2. Is this an equilibrium reaction? Yes. Okay, we tell by looking at the arrows. 100% it's an equilibrium reaction. Right, and the KEQ is 48.8. Okay. So to construct our table, we're going to write an I, we're going to write a C, and we're going to write an E here. And it says, okay, we'll highlight this in red. Initial concentration of 0.040, 0.040. So that is the initial concentration. And the initial concentration of H2 and I2 are 0. Okay. So let's say we have a bottle of HI. Imagine. Okay. I want you to close your eyes and imagine you have a bottle of HI 0.040 molar. Okay. So that bottle of HI, hydrogen iodide, is not just hydrogen iodide. What else is in that bottle? Okay. Because it's equilibrium, you'll have some I2 and you'll have some H2, okay, besides the HI. Okay? So some of this reaction, I mean the reaction is equilibrium, you'll have reactants and products. All right. Because initially you have this, okay, and it does not go to 100% because it's in equilibrium. So which way will the reaction shift? Okay, it's going to shift this way because we have 0 of this and 0 of that. Initially we have this, but some of this reaction will go this way. So it's going to go shift this way to the left, and we're going to call it minus, but we will not call it minus x. Okay, because of the 2 here in the coefficient, it's minus 2x. What will this be if this shifts to the left? This will be plus how much x? X. x, because there's only 1 in here. Okay, what about here? Yes, 1x. Okay, so remember, this is the initial change. We said it's going to shift to the left because some of that hi will go back. Some of that hi will go back to give you h2 and I2. So the change here is going to be minus 2x here. Why minus 2? Because of the stoichiometry, because you have 2 of those hi's. And then finally at equilibrium, what will be the equilibrium concentrations? Okay, the equilibrium concentration of H2 will be x, I2 will be x, and HI will be 0.040 minus 2x. So these are the equilibrium concentrations. This is the equilibrium constant. Let's put everything in. We'll plug into the equilibrium constant. What is our equilibrium constant? Okay, HI. Okay, what should we do with that HI? You agree we have to square it? Products over reactants divided by H2 divided by I2. Okay? So now we're going to plug everything in. KEQ is 48.8. This is given to us. HI is 0.040. What should we do with that number? Okay, this is at equilibrium. What should we do with it? Okay, H2 is X, and I2 at equilibrium is X. So let me do some cleanup here. 48.8 equals 0.040 minus 2x whole squared divided by x squared. Alright, so now we'll solve for x. Once we solve for x, we'll plug it back in. So how will I solve for x? Okay, this is what you'll do on the exam. Okay, you're going to take the square root of both sides. Okay. Plugging this into the equilibrium mix constant. Substituting in, we're going to square root both sides to solve for x. Okay, this is the x that we want. Alright, so what's the square root of 48.8? Square root of 48.8 is what number? Okay, about 7, so 6.99. Okay, the square root of something squared is 0.040 minus 2x. The square root of x squared is just x. Okay. Now we should be able in the last couple of minutes to solve for x here. So here we have 6.99x equals 0.040 minus 2x. So do you guys know how to do this math? Okay, we're going to take this minus 2x, move it to the other side. 2x plus 6.99x is equal to 0.040. And what's 2 plus 6.99? 8.99x. equals 0.040. So x is going to equal to 0.040 divided by 8.99. And what is that on our calculator? I'm getting 0.0044 molar. I'll put in an extra digit here, 44 molar. Okay. So our final answer at equilibrium, our equilibrium concentration of H2 is going to be 0.00444. Our equilibrium concentration of I2 will be 0.00444, and our equilibrium concentration of HI will be 0.040 minus 2 times this. 2 times that. Okay, so let's quickly do that. So H2 at equilibrium. This is our final answer. H2 is going to equal to 0.00444 molar. I2 will equal to 0.00444 molar. And then HI is going to equal to, okay, what is 2 times this? Plus, so minus that, so it becomes the minus sign, plus 0.040, 0.0311 molar. And this is the answer. Plugging everything back in here. What you can do is you can take these equilibrium concentrations, plug it back in here, and what should it equal? It should equal 48.8. So if you put H2 here, I2 here, HI squared, put that in, it should equal 48.8. That's how you can check you get the right answer. 311. Okay, HI squared divided by 0.0044 and 0.0044 for 49.06, 48.8. I think that's good enough. Close enough. So you can always check your answer. Plug this back in to here, and it should equal to your equilibrium constant. All right, I am out of time. I will see you all on Friday. You take this, 0.00444, it's x. This is what x equals to. So it's going to be 0.040 minus 2x.
Okay.
So 0.040 minus 2 times this x.
Okay. Okay, well, I'm trying to see where I can find. Okay, so this part. I see why you did your arrows. So this goes over here.
Yeah.
Okay. And
That x,
and then goes here. Okay.
that's your I2.
Okay.
This x goes here, that's your H2. And this x goes here, which is 0.04 minus 2x, which is 2i, which is your
Lost you at that
HI. Okay, there you go. Go ahead.
I go ahead.
You want to take the test, right?
Oh, you said
Can you take it now?
yeah.
Okay, because I have to go. What's this?
Our lower portion.
From
I tried to find it
yesterday?
yesterday after I cut it.
Oh, okay. Yeah, go ahead.
Can you pause the recording? I gotta talk to you about something personal. Sorry.